Okay, well, welcome everybody to today's meeting of the CUNY virtual online set theory seminar. We are very pleased to once again have Tom Benhamou from Tel Aviv University speaking, and he will tell us about subforcings of the Tree-Prikry forcing. Okay, take it away, Tom.
Thanks again, guys, for having me here. It's a pleasure, and I hope you'll enjoy this talk. So this is in some sense a continuation of the two talks I gave last time, but I do not assume any of you attend these talks, so we're fine from this side. Of course, have to say this is a joint work with Moti Gitik and Yair Chayut. Most of the work here is a joint work with them, so I share the honor with them. So let me outline the talk. We'll start by giving some background motivation, then I'll give us the basic definitions relevant for this talk. And then we'll dive into the results. We'll start from non-results. Then we'll change our initial large cardinal assumptions, and we'll see that it affects the results, how it affects the results. Okay, so let us start with some background motivation. So in this talk, we will consider the possibility of projecting Tree-Prikry forcing on some distributive forcing notion, mostly distributive forcing notions. And a possible outcome of this work is the ability to iterate distributive forcing notion, as there are known techniques to iterate Prikry type forcing. Okay, so maybe this is a possible outcome of this work. Subforcing of the vanilla, the standard Prikry forcing, were studied by Gitik, Kopke, and Canove. It's a theorem I already stated my last talk, so let's recall what the theorem says. So if U is a normal measure over kappa, and G is a V-generic filter for the Prikry forcing with the ultrafilter U, and M is an intermediate ZFC model, then M is a generic extension of the Prikry forcing with U for probably another V-generic filter. So if you would like to consider what are the subforcings, what are essentially the subforcing of the Prikry forcing, then this theorem tells you that it is the same forcing, the Prikry forcing with the same ultrafilter U. This is the only forcing which generates intermediate models to this generic extension. And of course, this situation is under the assumption that the ultrafilter U is normal. And as we will see, this changes drastically when we remove the normality assumption and we consider the Prikry type forcing suitable for non-normal ultrafilters, the Tree-Prikry forcing. And we will consider intermediate models of that forcing under several large cardinal assumptions. So let's give some basic definitions. Of course, if there is any questions, you can stop me. Ask. I'm not. If I'm going too fast or anything, please stop me. Okay. Or too slow. That's also a possibility. So, given two forcing notions, P and Q, recall that a projection from P to Q is a function which satisfies three requirements. The first one is that it's order preserving. The second one is that for every P in the forcing P, and so we're forcing the Israeli style, namely larger or equal condition is stronger, it provides more information. Okay, so for every, it's the second requirement for a projection is that for every P in P, and for every Q above the image of P, there is a P prime above P, such that the image of P prime is above Q. This is the second requirement. And the fact that it's a projection requires that the image of pi is dense in P. Given these three requirements, we know that the forcing Q, the image of, the range of the projection, is going to generate intermediate models to the forcing P. And actually, there is a closer connection between generating intermediate models and projections.
Tom,
Yes.
sorry. The third point, you mean the image of pi is dense in Q?
Yeah, in Q, yeah.
Okay,
It's
okay,
a typo.
okay. All
Thank
right,
you,
okay.
sorry. Yeah, now I see that. Yeah, it should be Q, of course. Yeah, the range here is Q. Okay, so when the closer connection I can make between projections and the fact that some forcing generate intermediate models to a given forcing is the following. So given two forcing notions P and Q, we denote by B of Q the unique up to isomorphism, a complete Boolean algebra which contains Q as a dense subset. We can realize it as the algebra of regular open sets of Q. Again, this should be Q here, not P. Then the following are equivalent. The existence of a projection from pi to the Boolean algebra B of Q, and the fact that there is a P name H tilde such that for every V generic filter H for Q, there is a V generic filter G for P, which interprets that name as the generic. You have a name for a generic object for Q. This is equivalent for having a projection from P to the Boolean algebra extending, the unique Boolean algebra extending Q. Okay. So, but I can explain roughly why this proposition is true, but if you would like more information, you can either go to Shellach's book, The Proper Forcing. There is some explanations there, or the chapter by Uri Avraham in the handbook. It also has some nice presentation of all this topic. So let us present the Tree-Prikry forcing in, the generality we needed for our talk. So we start with I call it a tree of kappa complete ultrafilters. So basically it's a sequence of filters indexed by finite subsets below kappa, or finite increasing sequences below kappa, U subindex A. We assume always that these are kappa complete ultrafilters over kappa. So the definition of the Tree-Prikry forcing we denote by PTU, vector U, is the following. So conditions in PTU are pairs, T and capital T, where capital T is a subtree of finite sequences below kappa. It's a tree of height omega. I didn't say it here, but it follows from the rest of the definition with stem T, which is some U splitting. Namely, what is meant to be U splitting? So whenever you give me a node in the tree, which is above the stem T, the immediate successors of that node, namely all the ordinals below kappa, such that S concatenated with alpha belongs to the tree, is measure one with respect to the measure indexed by S. So if I can draw, not very nice drawing here. So you have the stem T, then you can extend, so you have the tree T, and whenever you extend to a node S in the tree, the immediate successor of S, all the alphas here, they form a measure one set with respect to the measure indexed by S. Okay, this is the idea. So whenever you give me another S prime, the immediate successor of S prime, they split according to the measure U S prime. Okay. This is what I mean by U splitting. Okay. So the order is defined as follows. So pair T capital T is less or equal than S capital S, if and only if the tree S is a subtree of T. And it follows from that the stem S belongs to the tree T, because it certainly belongs to the tree S. So basically this order is extend the stem from the tree T, and then shrink the tree to be the tree above the stem you chose S, and you can remove you can shrink it to be as long as it remains U splitting. This is the idea. Okay. In case you didn't change the stem, you didn't change the stem, you just shrink the tree. We denote this order by the direct extension order, and it's denoted by less or equal star. Let me give some facts about, it should be PTU, about the forcing we just presented. So first of all, it is kappa centered. Namely, you can present PTU as the union of kappa many sets, such that each set is directed. It's even less than kappa directed. Namely, given less than kappa many condition in a given conditions in one of the pieces, you can of the sets, the kappa many sets, you have an upper bound for those conditions. It does not add. Of course, the splitting is according to the stem. Yeah? You have only kappa many stems, so you kappa many possibilities for this t, small t. It does not add bounded subsets to kappa. This is due to the Prikry property that this forcing have, and the lesser equal star closure. This is the lesser equal star order is kappa closed. The second property is that it satisfies the strong Prikry property. So what is the strong Prikry property in this for this forcing? So for any condition T and capital T in the Tree-Prikry forcing, and dense open set D for the Tree-Prikry forcing, there is a direct extension T and capital T star, and some n less than omega, some level of the tree, such that whenever you extend T with a nod from the nth level of T star, you enter the dense set. Okay? The minimal extension using this T, the minimal extension over T with an element from the nth level of T star will enter your dense set D. Okay, this is another property. All the proofs for these properties can be found in, you can check the references. And there is a Matthias-like criterion for the Tree-Prikry generic, for Tree-Prikry generic sequences. You also this can be found in tree. I'm not going to use this bullet tree, so there's no reason for me to elaborate about it. Okay, so this is the basic forcing we are interested in. Let's present known results about it, about intermediates models of it. So it turns out, well, not surprisingly, that the structure of the intermediate models of the Tree-Prikry forcing heavily depends on the combinatorial properties you assume on your measure sequence, U. So we already seen Gittig theorem, but there is a more extreme situation, which is due to Kopke, Rasch, and Schlicht. This is in their situation. Actually, there are no intermediate models. It's like Sachs forcing in some sense. So assume that U is a sequence of distinct normal measures. So it's U alpha, alpha less than omega. So how it's in our context, it basically means that we view the tree U, that we should index it by a finite sequence. Well, the measure only depends on the maximal element of that sequence. So given a measure of sequence, kappa distinct normal measures, then for every V generic filter G for the Tree-Prikry forcing, there is no proper intermediate model V between the ground model and the generic extension. This is their result. So this is a very extreme situation in which you do not have intermediate models at all. Of course, the assumption here is quite strong that it is a kappa sequence, and that these are distinct normal measures. Okay. The other extreme would be a situation where the Tree-Prikry forcing have a large variety of intermediate models in terms of many type of forcings which generate intermediate models to it. This would be the other extreme. So what should we expect of such a forcing that creates an intermediate model for a Tree-Prikry forcing? So if it does not add a new omega sequences, namely if it's sigma distributive, then it should be at least kappa distributive. The reason is that the PTU does not add fresh subsets to ordinals of cofinality less than kappa. Okay, so if you have a ground model ordinal which has cofinality less than kappa, then the Tree-Prikry forcing wouldn't add to it a fresh set. And this is enough to guarantee that the forcing is kappa distributive. Okay, so this is one thing we should require. Also, we'll see later, a projection of a kappa-centered forcing is kappa-centered. So we should ask for that the forcing is kappa-centered, and that the cardinality should be at most 2 to the kappa. Okay. So in the next slide, we will see that under large cardinal assumption, we consistently have some variety of intermediate models. So let's start by the first large cardinal assumption we would like to pose, and this is the kappa being kappa compact. So what is a kappa compact cardinal? Kappa is called a kappa compact cardinal if every kappa complete filter over kappa can be extended to a kappa complete ultrafilter over kappa. So we are only talking about kappa complete filters over kappa, not over some other lambda. Okay. So this is a kappa compact cardinal. What does this large cardinal property has to do with our problem? So apparently it's deeply connected, as the following theorem suggests. So suppose that P is a sigma distributive forcing notion of size kappa. Then you have the following equivalence. The first is that there is a projection from for some tree of kappa complete ultrafilters vector U. There is a projection from PTU to B of P. This is one statement, and the statement which is equivalent to it is that for every condition P in P, the filter dP of P, which I'll say in a second what it is, can be extended to a kappa complete ultrafilter UP. So what is dP of P? dP of P is the filter of open subsets of P which are dense about P. So assuming, for example, that P is a kappa distributive forcing notion, this exactly says that dP of P is a kappa complete filter. Yeah, because what does it mean to be kappa distributive? It means that the intersection of less than kappa many dense open sets is dense open. Okay, so
excuse me, Tom, could I just ask you another question? Sure. I didn't quite understand why how you came up with this idea of sigma distributivity. These Tree-Prikry forcings, don't they always add a new omega sequence? Or
yeah, but if you consider an intermediate model of it, then it would be interesting if it wouldn't add a new omega sequence.
See. Okay, all right.
Yeah, you're right. The Prikry forcing itself, no, it's a good point. The Prikry forcing itself, it adds an omega sequence. So it is certainly not a sigma distributive forcing. But we're interested in a very different situation where you get an intermediate model where you don't have a new omega sequence.
Mm-hmm.
Okay.
But still something new is added.
Yeah,
I see. Okay, all right. Thank you.
Okay, so so if you consider only such forcings that are sigma distributive, which namely do not add new omega sequences, then and you assume that they are of size kappa, then you have the equivalence that the Tree-Prikry forcing projects onto the complete Boolean algebra generated by this forcing, and the fact that you can extend the kappa complete filters, okay, so in this case, sigma complete filters dp of p to a kappa complete ultrafilter up. So the corollary of this theorem is that if kappa is kappa compact, then every kappa distributive forcing notions of cardinality kappa is a projection of the Tree-Prikry forcing, because you can always satisfy the second requirement. So as we said, if you have a P which is sigma distributive, I roughly explained why it is kappa distributive, which will make these filters dp of P kappa complete filters, and since P is of size kappa, this would be a kappa complete filters over a set of cardinality kappa. Then by the large cardinal assumption about kappa, this would be extended to a kappa complete ultrafilter over this forcing P. And therefore, by the theorem, the Tree-Prikry forcing would project onto the complete Boolean algebra generated by this forcing. Okay, this is so this is the other extreme. When you have a very large cardinal assumption, kappa being kappa compact, then you have a large variety of intermediate models. Every kappa distributive forcing of cardinality kappa can be an intermediate, can generate an intermediate extension to Tree-Prikry, generic extension. Okay, so far so good. Any questions?
So so this is basically saying for every kappa distributive forcing, you can construct some sequence U such that it is an intermediate model there. So can you maximize it, like somehow have one Tree-Prikry forcing that has lots of?
This is a good question. So actually, Morris Gittig proved that you can have one Prikry type forcing, namely you construct an extender such that forcing with the extender-based Prikry forcing with that extender, you generate all the kappa distributive forcing. You have all the kappa distributive forcing notion of cardinality kappa as intermediate.
It's pretty cool. Okay.
Yeah. So this is a result by Moti several years ago. Yeah. Okay. So let us try to improve this assumption of kappa being kappa compact. So Gittig, this is quite strong assumption. Gittig proved that if kappa is kappa compact, then there is an inner model with a wooden cardinal, so it's quite high. The question is, can this assumption of kappa compact be relaxed? So note that we really don't wish to extend every kappa complete ultrafilter, but just kappa complete ultrafilters of the form dp of P, which are quite definable. This is if you have a model where you have P and P, then you can define this filter dp of P. So there are quite definable filters, and these are the one you would like to extend. And the assumption that kappa being one extendable, which I wouldn't want to define here, is enough to guarantee that you can do that you can extend such filters. It requires, of course, a proof, but it's not a very long one. But there is a very short argument that explains why one extendable is enough. And roughly speaking, this is because of the fact that we wouldn't want to extend every kappa complete ultrafilter, every kappa complete filter, but rather kind of relatively easily definable ones. Okay, now the hardest theorem of this of the paper of our paper with Yair and Moti was the following one, and it gives actually a lower bound for the possibility to extend to the fact that kappa distributive forcing notion of cardinality kappa are intermediate to the Tree-Prikry forcing extension. So the theorem says that if consider the forcing Q, the forcing Q is the forcing for shooting a club through the singulars below kappa. Okay, so if you shoot a club through the singulars below kappa, you make kappa not malo. Under our assumption, kappa being at least measurable, this is a force. You force it by bounded closed sets. This is the forcing basically, with the end extension. Under our assumption that kappa is measurable, at least measurable, then this is of course a forcing notion of cardinality kappa. And it is less than kappa strategically closed. Okay, this is also not a very hard argument. So in particular, it is kappa distributed. So Q, the forcing for shooting clock through the singular is below kappa. Under our assumption, it is the kappa distributive forcing of cardinality kappa. It is more than that. It is a less than kappa strategically closed forcing of cardinality kappa. So we have this forcing, and what the theorem says is that if you can extend the filter D of Q, which is the filter of dense open subsets of Q, then either there is an inner model where there exists a lambda with a mutual order lambda plus plus, or that the mutual order of kappa in the core model K is at least kappa plus. Okay, so you get the consistency of something larger than a measurable cardinal. Okay, this is the theorem, and it actually gives a lower bound for something not only for the kappa distributive forcing notion, but for the less than kappa strategically closed forcing. Okay, so this is an additional class of forcing to consider, of course, in this situation. And the theorem, the proof is quite long, but the idea is that if you have such a filter, D of Q, then if you can extend this filter D of Q to a kappa complete ultrafilter, then you can take the elementary embedding with that ultrafilter, and when you analyze it, you get a situation where you must when you restrict it to the core model, it must be quite long. So and using either there exists lambda such that out lambda equal lambda plus plus, and then we're done. But if there is no such lambda, then we can apply the mutual indiscernible analysis, and then by this analysis we can show that when you restrict this extension, this elementary embedding using this kappa complete ultrafilter, which extends your Q to the core model, it must be an iteration of the core model using the measure in it, and it's quite a long iteration. This is what we prove in our theorem. But it's very vague, what I just said.
So, Tom, can I ask a question?
Sure. I don't know who's asking, but yeah, sure.
So, okay, I'm understanding this theorem to say that if I want, let's see, if I want to have an intermediate model of a Tree-Prikry extension for this club shooting forcing, then kappa should have been quite large, or there are very large cardinals in the back.
There are large, yeah, okay. That's what this theorem says.
Do you have results? So what if I ignore this problematic club shooting forcing? What if I just want forcings that are maybe preserved stationary subsets of kappa, or have some kind of...
We'll get to it. We'll get to it. This
okay.
The next step would be to consider to remove this large cardinal assumption and see actually what other forcing, what can we say in this situation where we don't have this large cardinal assumption. Okay. But that's where we're heading exactly. So all right. Thank you for preparing the ground. Other questions before I'm moving? Okay, so let us change the large cardinal assumption. Let's just move to the other extreme where we work under the minimal large cardinal assumption, which is obviously measurable cardinal. So we assume now only the existence of that kappa is a measurable cardinal. Can we say that there is a non-trivial subforcing or the Tree-Prikry forcing? I mean, non-trivial, I mean, not Tree-Prikry type, that's what I mean. If we assume the existence of a measurable cardinal, well, this was a theorem in my master's thesis that we proved that if we assume GCH and we let kappa be a measurable cardinal, then there is a cofinality preserving forcing extension N of the ground model V, in which there is an ultrafilter W. Of course, it would be a non-normal ultrafilter W, such that forcing with PTW, so what does it mean to force a Tree-Prikry forcing with a single W? It means that the splitting in each level is according to the same measure. So PTW, so if you force PTW over N, you add a kappa Cohen real. So a generic function for the forcing add kappa 1. Okay, so this is only under the assumption of a measurable cardinal. Let us prove this theorem. Okay, so the preparation, you prepare the universe by performing an Eastern support iteration of length kappa, such that at every step, which is not inaccessible, we perform the trivial forcing. And at inaccessible steps beta, the Q beta is a P beta name for the lottery sum, which I'll explain what it is in a second, of the trivial forcing and shooting and adding a beta Cohen real, namely add beta 1. So what is the lottery sum? You basically have two incompatible elements, basic elements. Over one, you force the trivial forcing, and over the other, you force the Cohen forcing, okay? The beta Cohen forcing. Okay, so this enables you somehow to choose what to force when you construct generic objects. Okay, let G kappa be a V generic filter for that iteration, P kappa. So in G kappa, we can think about it. There are many places which the lottery sum chose to perform the Cohen forcing, and then there are other places where it chose to perform the trivial forcing. And denote by N the generic extension by this G kappa. And let U, now we would like to take a normal measure from the ground model and extend the embedding. So let U be a normal measure over kappa, and J1 we denote the elementary embedding associated to that normal measure. So this is an elementary embedding from V to MU. We denote by kappa 1 the image of kappa, the J1 image of kappa. And we would like to extend J1 or JU to J1 star, from VG star to MUH, where H would be some MU generic filter for J1 of P kappa. So how do we do it? This is where we exploit the fact that it's a lottery sum. So J1 P of kappa is we denote it by P kappa 1. It's basically by elementarity, it is an iteration of length kappa 1, where at each inaccessible we perform the lottery sum. This is the recipe for this iteration P kappa 1. And the generic we have for P since kappa is the critical point, this starts by P kappa, by the same iteration. We have already have a generic for, so we can take for the generic up to kappa to be G kappa. Okay. What do we do at kappa itself? At kappa itself, we cannot force we cannot hope to have in VG kappa a Cohen generic forcing a Cohen generic forcing function for kappa, because the MU side and the VG side see the same dense subset for at kappa 1. So there is no hope to find such a function. But fortunately, we have the lottery sum, so we can choose to force the trivial forcing at kappa itself. And by doing that, if we choose to work above a condition that forces that we force the trivial forcing at kappa, we gain sufficient closure above kappa, and here we explode GCH, to construct a generic inside VG to the remaining of the forcing. Of course, this is a strategic, very strategically closed forcing, and we can do it in the, we can construct a master condition sequence in the usual way. Once we choose at kappa to force the Cohen forcing. Okay, so I didn't do the cardinal calculation here, but I did it this morning again, and I think it worked. So, and it went through several referees, so I think it's okay. Okay. So let us define now, let's consider the normal ultrafilter after we extend J1 to J1 star. So certainly, if you derive the measure generated by kappa, then since we chose at kappa to force the trivial forcing, this concentrates on points where I forced the trivial forcing below kappa. You have the measure one set of points where you don't have a Cohen function prepared for. So what do? The idea is to move to the second ultra power. So back in V, let us consider the second iteration of U. Okay, so we have J of J1 of U from MU to MJ1 of U, the second iteration. We denote by J2 the composition of these two maps, K2 the second image of kappa. And now let's know that from the point of view of V, there are still only kappa plus many dense subset of P kappa 2 in MJ1 U. Okay, this is the kappa 2 is still a cardinal of size kappa plus from the point of view of V. And the forcing now P kappa 1 kappa P kappa, so the tail now that we should take care of P kappa 1 kappa 2 is kappa closed, no matter what we choose to force on kappa 1. It's kappa plus closed, I mean, from the point of view of V. And actually here, we can choose on kappa 1 to perform the Cohen force. This is the point. Okay, so maybe let me just, I think this is the point to sketch something. So you have here a kappa, which is sent to kappa 1, and then it's further sent to kappa 2 using the second iteration. Here you force the generic G kappa. So you take the same generic here, G kappa. On kappa itself, here you do the trivial forcing. So we don't have need to generic, and you use the fact that this is a ordinal of cardinality kappa plus in the point of view, from the point of view of kappa and the closure to kappa sequences in order to generate here the remaining generic object. So G, let's call it G kappa 1. And now this is also of size kappa plus. This is the point. So here we can choose to force a Cohen forcing. So we like to note it differently than we do. So add, here we force add kappa 1 with respect to the model here below. So it's on M prime, which is something obtained here. So here we have the same thing. We have G kappa, we have G kappa 1. Here we will force a Cohen function, and here we complete it in some way using the strategically closure of the forcing above. Okay, this is the picture. And all this filter here, which seems quite long, but it's not very long because this is a cardinal of size, this is an ordinal of size kappa plus, can be constructed inside VG. I hope I convinced you. Back to the here. Okay, back to the proof. Now the point is that that once we extend J2 to J2 star, when we choose the coin part in the lottery sum for Q kappa 1, then we can define the following measure, the non-normal measure derived from kappa 1 using J2 star. And this measure will concentrate, we'll have a measure 1 set which concentrate on ordinals alpha below kappa, inaccessible ordinals below kappa, over which you perform the Cohen forcing. Okay, so we have a Cohen function prepared. So we have a measure 1 set Y with respect to W, such that for every alpha in Y, there is a function f alpha, a Cohen function f alpha, which is added by G kappa. So I think of it in the following sense: you prepared many initial segments of an eventual Cohen function over kappa. So we have many initial segments, and then the Tree-Prikry sequence is the glue needed to put them together. This is what will happen here. So now if I force the Tree-Prikry forcing with this W over N, and I denote by Cn the n-generic Tree-Prikry sequence added by this forcing. So by standard arguing, there is some point from which on all the Tree-Prikry sequence enter this measure 1 set Y. Okay, this is a basic property. So I have the function, the Cohen function FCN already defined. It's ready for me, so I can use it, and I can now it remains to see that if I define the following function, so it should be small c here, not capital C. So I take the first part is FCN0. So the Cohen function I will define over kappa is going to look like this. So I have up to Cn0, it's just a function f Cn0. Then in the interval Cn0, Cn1, it's the function f Cn1 restricted to that interval. Okay, and then here the up to Cn2, it's the function f Cn2 restricted to that interval, and so on. This would generate a function f from kappa to, if you want 2 or kappa, it doesn't matter. We define or you want to define your add kappa 1 forcing. And it remains to see that this is an n-generic function for the forcing add kappa 1. I'm not going to go into details why is it n-generic, but it's not a very long argument to see that this f is actually n-generic. Okay. This is the proof. Are there any questions before I'm moving ahead?
Yes, could you maybe explain why it is important in this context that it's the tree version of the Tree-Prikry forcing? Like if you use just the regular Tree-Prikry forcing, that would not.
So the regular. The question is, what do you mean by the regular when you have a non-normal measure?
Okay, I was just thinking naively, like just use the definition of the regular of Tree-Prikry forcing, but drop the assumption that it's a normal measure.
Yeah, so you have to be careful there because you don't have diagonal intersection. So you need some. You can modify it to be a regular one if you play with the. We will do it actually later. Mm-hmm. If you have some requirements about the projection. You have some function representing kappa in the power by W. If you do that, it's the same. This is what I mean actually by PTW. Mm-hmm. Okay. They are forcing equivalent, these two forces.
I see. I mean, if you don't assume normality, of course, some properties of the usual Tree-Prikry forcing will fail, like probably the Tree-Prikry property and stuff like that. But you could still define it. But I guess it would not. Yeah,
it will do bad things. Yeah, you need to be just your definition should also involve this pi, and then you're okay.
Okay.
Okay. Okay, so what I'm going to move now to the next part, which is called masterable forcing. So the question is, okay, we've seen that under the minimal large cardinal assumption, it is consistent that the Cohen forcing is an intermediate to the Tree-Prikry forcing. So as a corollary from that, we get that since, okay, so first of all, a lemma, well-known lemma that every kappa strategically closed forcing of cardinality kappa is actually a projection of the Cohen forcing. And therefore, since we can project, we can consistently project onto the Cohen forcing, we can consistently project onto every kappa distributive forcing of cardinality kappa. Okay, this is a corollary from that. So the next natural class to consider is the less than kappa strategically closed forcing, which we've already encountered, and we've seen it requires large cardinals. However, a result by Dan Vellman proved that if you have something called a Jensen square is one of the infinitely many variations of squares, which is, as it's stated, due to Jensen. I'm not gonna explicitly say what sort of square it is, but it's a very similar one to the one you know, only it sits on kappa itself, okay, not on kappa plus. And what it proves that if you have such a square, then every less than kappa strategically closed forcing is actually kappa strategically closed forcing. So you can imagine that if you have some sort of square, and you have, for every lambda below kappa, you have a strategy, then the square somehow enables you to glue this strategy together to a strategy over kappa. This is the intuition, heuristic. So this is a result by Dan Vellman. And actually this provides the same way that the Cohen forcing is maximal in the sense of it projects onto every kappa strategically closed forcing cardinality kappa, then also there is a maximal forcing which projects onto every less than kappa strategically closed forcing of cardinality kappa, which is the one that adds a Jensen square. Okay, so we proved in our paper that this is a maximal forcing for this class. So if you would like to project onto every less than kappa strategically closed forcing of cardinality kappa, it's enough to project onto the Jensen square forcing, adding the forcing which adds a Jensen square. Okay, so the question is, under the minimal assumption that kappa is measurable, what is the class of forcing P which can be intermediate to Tree-Prikry forcing? We've seen that the Cohen forcing is, but can we find other forcings? So this class, we call it the masterable forcing. The technique of the theorem we just proved for Cohen forcing, we can modify it to abstract settings. And this defines and actually generalize this result to a more sophisticated one. So the class of masterable forcing, which we denote by n kappa, is defined by properties for which the argument we gave for Cohen forcing generalizes. So what is the definition of a masterable forcing? So a forcing notion Q is called masterable if Q is kappa distributive forcing of size kappa, and there is a further forcing notion R, a name for a forcing notion R in the generic extension by Q, such that in the model V Q star R tilde, there is an elementary embedding of VQ to some M with critical point kappa. So there is a generic elementary embedding of VQ of the model VQ, definable in a further forcing extension by this forcing R. And the requirement is that this forcing Q star R tilde has a dense subset of size less or equal than kappa. So, and it is less than kappa strategically closed. Okay, this is the requirements from a masterable forcing, and apparently these are enough to generalize the idea of the theorem we just proved for Cohen. So, for example, the Cohen forcing is masterable. You can just take R to be the trivial forcing. So if you take R to be the trivial forcing, then certainly in generic extension by Cohen, you can lift some, you have a normal measure in the ground model, you lift embedding to the generic extension. And of course, Cohen forcing is of size kappa, so it has a dense subset of cardinality less or equal to kappa. It's kappa closed, so it's certainly less than kappa strategically closed. Okay, so this is, but of course we're going to use, I mean, there are other forcing notions for which are masterable, for which this R is non-trivial, Otherwise, this wouldn't be interesting. Okay, so the theorem, of course, is that generalization, what we just proved. So assume GCH and assume that kappa is, what time is it? Oh, when did I start? How much time? Will you start at 7:30? Okay, I still have
almost an hour so far.
Okay. Sorry, it's a bit late here, so not. Okay, assume GCH and let kappa be a measurable cardinal. Then there is a cofinality preserving extension in which every masterable forcing, every Q belongs to the class of masterable forcing, is a projection of the Tree-Prikry forcing. Okay? And this is, again, under the minimal assumption of kappa being measurable cardinal. I'm not sure, I have the proof here, sketch of the proof. Maybe I'll go back to it only if people would be interested. I still have something I would like to show to you, and so let me just skip this proof and maybe come back to it later if you're interested. So let me just state some fact about masterable forcing. So first of all, it is closed under complete subforcings, and it's proven to consistently include forcing notions which are not projections of the Cohen forcing. Otherwise, it wouldn't be interesting. For example, you can think about the forcing which shoots a club through a stationary set of singulars. Okay, this is of course impossible if you just say that, because I know that only the forcing that shoots a club through the stationary set through the singulars is requires more than measurability. Yeah, but for example, the forcing which shoots a club through the stationary set of singulars, which is of measure 1 with respect to some normal measure. So I corrected the problem. So you take any stationary set, which is measure 1 with respect to some normal measure, which consists only of singulars, then the forcing which shoots a club through this stationary set is going to be masterable, is masterable. Okay. And the question is that, so how large is this family? Well, we also proved that it is consistent that there are forcing notions which are kappa distributive, which are not less than kappa strategically closed forcing, nor masterable. So it does not cover all the possibilities of kappa distributive forcing notions. Okay. Oh, I have a typo here. So. Okay, so the last slide, the last thing I want to talk to you about is this another assumption. This is a very recent work. So what limitations do we have on the projection of the Tree-Prikry forcing? So we said it should be kappa distributive, of course. If it's sigma distributive, then it should be kappa distributive. And in terms of cardinality, well, it should be at most 2 to the kappa, and also kappa centered is essential. So this is a two-line argument why this is essential. So if P is kappa centered, then it is the union of kappa many sets. Each AI is a directed set. And if pi from P to Q is a projection, then assume it is onto, okay? So otherwise the fact that the image is dense it's not problematic here. So Q would be the union of the pointwise image of each part of the sets which witness the fact that P is kappa centered. And each pi pointwise image AI is also a directed set, since pi is order preserved and the AIs are a directed set. So if you give me pi of x1 and pi of x2 in pi pointwise image of AI, where x1 and x2 are in AI, then there is x3 above them because AI is directed, and the projection of that x3 would be above pi of x1 and pi of x2. So it's directed. Okay, so as a corollary from this, we get, for example, that add kappa plus 1. So if you would like to add a Cohen function to kappa plus, is not a projection of the Tree-Prikry forcing because it's not kappa centered. Okay, you have if it would be kappa centered, then you, since there are 2 to the kappa many functions from kappa to 2, then okay, so it's not kappa centered. However, there is another forcing of size kappa plus to consider, which is adding kappa plus functions to kappa, namely forcing a function, namely the forcing which have partial functions from kappa plus to say 2 of cardinality less than kappa, and this is kappa centered. I'm not proving it's kappa centered. It will follow. I mean, there is an argument for this, but I'm not going to go into it. So in a very recent joint work with Gittik, we think that we can actually get that consistency that add kappa kappa plus is a subforcing of the Tree-Prikry forcing. So there is so maybe it's surprising because the work done so far in this area always assumes that considered kappa distributive forcing of cardinality kappa. And here we think that the cardinality kappa is, we think that the cardinality kappa can be removed. So actually we present here a forcing notion which is quite natural to consider, which is of size kappa plus and is kappa distributive, which is going to be a subforcing of the Tree-Prikry forcing. So it gives a new variety of possibility. I mean, it opens the door for many other forcing notions to be subforcing of the Tree-Prikry forcing.
Could I just ask something that I have been confused about from the beginning?
Yeah.
So there are these 2 notions that seem to be relevant. One is whether there's a projection from one forcing to the other, and the other one, whether the other forcing is completely contained in so a complete subforcing of the first one. Is that those are different notions, right? Or
I think that to be a projection, I mean, when I say something is a projection of something, I mean it projects onto the complete Boolean algebra which generates.
Right.
So, and I think this is, if I'm not mistaken, I think this is equivalent to being a complete subforcing.
Okay, I see. Okay.
I think.
Okay, it should be.
I mean, my only interest is to generate. I'm talking about projection of forcing and non-complete subalgebras because complete subforcing because it's. I mean, it's more natural to think about, for me to think about projections, and
okay,
and therefore, and what I'm interested in is to generate intermediate models. And I know for sure,
yes.
but I know that when you have a forcing notion which is a projection of another one, then it certainly generates intermediate models.
Sure.
Okay.
I think a good strategy for questions like this is to forget about forcing and just say a complete embedding of the regular open algebras. And at this level, Boolean algebras are easy. When you actually want to build a forcing, that's a different story.
Yeah.
Right. Yes, that's true in so many cases that it makes things kind of clearer when you work with for the theory, if you work with the complete Boolean algebra.
Yeah.
The theory is Boolean. All the almost all the examples are based on forcing notions instead.
Thank you for that comment. Okay, so here we talk about we would like to concentrate on the forcing which adds kappa plus many Cohen functions to kappa. And what I claim now is that we what we think actually happens is that it's consistent that it is a projection, or at least its complete Boolean algebra is a projection of the Tree-Prikry force. Okay, this is done. I mean, the way our idea is using a non-Galvin ultrafilter. So let me explain what it is. So definition: a kappa complete ultrafilter U is called a Galvin ultrafilter if it satisfies something I call the Galvin property. If for every kappa plus many measure one sets with respect to U, so a list of kappa plus many sets in U, you can extract kappa many out of them for which the intersection lays in U. So if kappa is kappa complete, certainly every less than kappa many sets the intersection is in U. Kappa many of them, well, usually this is not the case. And even if U is normal, then you only have the diagonal intersection. But the Galvin property says that given any kappa plus many sets, you can always find kappa many from this. You can always extract kappa many out of them for which the intersection lays in U. Okay, so this is the Galvin ultrafilter. Galvin proved that normal ultrafilters are Galvin, satisfy this property. And we would like to use non-Galvin ultrafilters, so non-normal ultrafilters. So for adding kappa plus many coins to kappa, it is necessary actually to force with a non-Galvin ultrafilter. This is a proposition. So let U be a Galvin ultrafilter. I think this is a very nice connection, by the way, generally speaking about generic extensions by Prikry forcing. This is something Gitti calls the density of old sets. So let U be a Galvin ultrafilter and G a generic extension with the Tree-Prikry forcing with U. Then for any subset A in the generic extension, say a set of ordinal or just any set which is included in the ground model of cardinality kappa plus will always contain a subset from the ground model of cardinality kappa. This is saying that sets of cardinality kappa are dense in sets of cardinality kappa plus. This is the cardinality of old sets. Okay. So usually we do the opposite, right? When you have some CC assumption on the forcing, then you can cover the set. Here we want a subset, not a cover. Okay. So proof. So suppose otherwise, and let A alpha less than kappa plus be an enumeration of A, and A alpha tilde alpha less than kappa plus be names for this enumeration. So on one hand, translating the assumption A, there is no B in V of cardinality kappa, which is a subset of A. This is the assumption of the otherwise. And on the other hand, for every alpha less than kappa plus, we can find the condition P alpha, and now I'm getting to, so T alpha and A alpha, and this is Gunter's remark earlier, that we can actually assume this A alpha is a set in U. So this is the comment here, this A footnote, such that P alpha actually decides the value of A alpha tilde. Okay. Then there is so we have for each name A alpha, you have kappa plus many of them. You find a condition which forces this, which decides this value. Maybe incompatible elements. I don't care. Okay. Then I can stabilize these T alphas. Okay, so I can find kappa plus many indices. So there is a set X, a subset of kappa plus of cardinality kappa plus, and some T stars, such that for every index X in alpha in X, T alpha is actually this T star. I can stabilize this value. And now I consider this measure one sets, the A alpha in X. These are kappa plus many sets because the size of X is kappa plus. So my assumption that U is Galvin will secure that there is a subset Y of X of cardinality kappa. There are kappa many of these which intersect for which the intersection is going to be measure 1. So there is a Y subset of X of cardinality kappa, such that the set A star, which is the intersection of A, Y, Y in Y, and capital Y, belongs to U. So now consider the condition T star A star. This condition lays above kappa many P alphas. Which one? The one for each alpha which belongs to Y. And this condition, it decides kappa many values of the A alphas. So this is a contradiction because we can now find a subset in the ground model of this initially, the set we started with, this set A. Okay. And actually there is a closer connection between the Galvin property and density of old sets. So it goes to many other levels. So you have some lambda regular and some U below it. And you would like to say, you would like to ask, is sets of cardinality mu, are sets of cardinality mu dense in new sets of cardinality lambda? Can you always ensure that a set of cardinality lambda in the generic extension includes a set of cardinality mu from the ground model? So this actually is equivalent to some variation of the Galvin property on the ultrafilter you have. You're forcing this. I'm talking about only Prikry forcing. Yeah. And so this is what I'm saying. Actually, the other direction is also true that if you have this density of old set, then you must be Galvin. Okay, but this is just a remark. So the outcome of this, so the corollary from this proposition is that if U is Galvin, then U does not add a generic for add kappa kappa plus. And the reason is that if f from kappa plus to 2 is add kappa kappa plus generic function, then you consider the set of all the alphas below kappa for which the function assigns the value 1. And by density argument, you can prove that this set actually has no V subsets of cardinality kappa. Because any condition in any approximation of F should be of size less than kappa. And if A would have a subset of cardinality kappa from the ground model, we can always extend the condition, which has domain less than kappa, with a condition from this set of cardinality kappa and assigns to it the value 0. Okay, so this is always possible, and therefore we don't have A witnesses the fact that there is no density of old sets of cardinality kappa, so you cannot be Galvin. So it used to be theorem here like 2 days ago, but then we found a bug in the proof, so now it's a conjecture. Starting from measurable cardinal, it is consistent that there is a non-Galvin ultrafilter U such that forcing with PTU adds a generic for add kappa kappa plus. What I said at the beginning, that we think we actually can get the consistency. So it's a conjecture, but actually there we believe it is true, and we are on the verge of proving it, but still lacks some small details, which hopefully will be resolved very soon, and we'll upload some version of this proof to the archive. Anyway, I think that this is all I wanted to say. Unless I attach some references for proposition I stated along the way. So thank you very much, guys, for your attention. And that's it.
Right. Thank you very much.
Thanks very much, Tom. Really good talk.
Very nice talk as always.
Thank you. Are there any questions? Would love to answer the questions.
There was one slide where it just went too fast for me, and I didn't quite understand what something about it sounded absurd. Like you said something about some set of singular cardinals having measure 1 with respect to some normal.
I had the same question. I didn't understand that. I think it was slide 21.
Let's go back to it. Oh, yeah. Yeah, this one. So what I claim is that if you consider take some stationary set, so if it belongs to a normal measure, then it's stationary set, right?
Mhm.
So to take any set which belongs to a normal measure which consists of singulars.
Yeah, that's the problem.
Yeah, that's the problem. How
Yeah,
can
yeah.
how can a set of consisting of singulars be in a normal measure?
Yeah.
Point.
Like the regular cardinals
Yeah, you're right.
have
You're
measure
right.
one.
There is a problem here. Maybe I'm not stating it correctly. To check it. Yeah, you're certainly right that this is absurd. I should probably I'm saying something incorrect here.
If it's not a normal measure, then it's not a problem, right?
Yeah, if it's not normal measure, it's not a problem. But I think it's important for it to be. There is certainly a problem with the formulation here. You're right. That's
Okay.
not correct.
Okay.
Thank you. I will send an improved version of these slides, and hopefully we'll find the correct formulation of this.
Okay. Right. Great. Any other questions?
Can I think right at the end, like maybe back a couple, when you're talking about the Galvin,
Yeah.
right? I think the one right before this. Oh, at the end, it says, actually the other direction is also true, that if there is no such subset in V of G, then you must not be Galvin.
I mean, the other direction would be that if you have the density of all set, I probably didn't write it correctly, but I think I said it when I said it correctly, and it's written incorrectly.
Okay,
So
I thought.
you're probably right. What I mean is that if you have the density of all set, then U must be Galvin. So if U is not Galvin, then you can always ensure that there is a set of size kappa plus, which does not contain an old subset of cardinality kappa. That's what I mean. Yeah, but certainly what's written here is not correct. You're right.
Okay.
This would also be corrected in the improved version of my slide. I'm sorry.
All right. Sounds like everybody is satisfied. Okay.
Thank you very much,
All right.
guys.
Great. Thank you.
Very
And have a good night.
Thank you so much.
And a
Great.
nice weekend,
Bye.
everybody.
Thank you. Thank
Right.
you. Bye-bye.
Bye.